right, this section is very similar to our previous one about testing a claim about a proportion, but this time we are testing a claim about a mean. So as we go through this, it'll be very similar to the last one. When we're dealing with the mean, though, if you've got X bar, don't forget that's the sample mean, and S is the sample standard deviation. And if you see this mu with the little sub X bar, really most of the time we just deal with mu, and mu is the population mean. The sub X bar is the mean of the sample distribution. It's really more than you have to deal with right now. So just associate mu with the population mean. Now, when we are going to test claims about the population mean, the sample has to be a simple random sample. So you've got to make sure of that first of all. And then the second one has an or in it. So it's got to be simple random, and it's got to be normally distributed, or you have to have a sample size bigger than 30. So simple random, n is greater than 30. That works. Simple random, normal distribution, that works. But you're going to have to verify that each time, or you might have to select on your homework that you can't do it, or it'd be meaningless. There's a formula for getting a test statistic, and we're not going to have to use that formula a lot because really we're going to be using technology, but I always try to share some of those basic formulas for those of you that maybe don't have the right sort of technology or the graphing calculators that we want. But we will be using the student's t distribution. So that's not the normal distribution, it's the student's t distribution, which is why our test statistic is t. Now, the reason we are using t is really just quite simply because we don't know sigma. So that's what's up here in yellow. So when you don't know sigma, you have to use t. And if you know sigma, it's a different thing. That's one of the things you'll watch for. Now, normally, we don't know sigma. Sigma is a standard deviation, but S is a standard deviation from a sample. So when you do a survey, take a poll, do some research, or look at past data, you can take a sample and get an S. But it's highly unlikely you actually have the standard deviation from an entire population. That would have to typically be a pretty small population. The normal expectation when you're doing this testing a claim about a mean is, even though we may be looking at a simple random sample with a normal distribution, if we don't know sigma, you're using t. Okay, I cannot stress that enough. There's also something in the t distribution that's called degrees of freedom. And your degrees of freedom for this will be n-1. n-1 for your degrees of freedom. So if you had a sample of 35, then your degrees of freedom is 34. What happens on that t distribution is that as your degrees of freedom gets higher, as your sample size gets higher, it gets closer to being a normal distribution, but it's not exactly the same, even though it is kind of bell-shaped. Okay, so you can see what I'm just talking about right here on this little graph. The black one is the normal distribution. And then the degrees of freedom, different degrees of freedom, are all these different color graphs. So what happens, let's look at the purple one. If you have a small degree of freedom, it's going to be bigger than the normal out in the tail area and smaller than the normal in the center area. But as you increase those degrees of freedom, it gets closer on both sides. It'll like lower itself on the tails and rise up in the center. So the higher degree of freedom, the closer it is to being the normal distribution. So about the t distribution then, it is different for different sample sizes. Okay, you don't always get the exact same thing. That does mean that you cannot memorize or shortcut on finding those critical values. You'll have to recalculate it every time because it depends on your sample size. It does have the same shape as the standard normal distribution. It's a little bit wider, even though this graph stops here, so it would continue to lower as it went out on the edges. So it's going to be wider, and that's just because we're going to have a bigger range, a bigger standard deviation because you're having to use S to estimate sigma because you don't know sigma. It does have a mean of 0, but the standard deviation is going to change. So you're not going to say that it's just 1, it's going to be bigger than 1, which is part of why our graph gets wider before it gets low. As n gets larger, it gets closer and closer to it. The t-distribution is robust against a departure from normality. That is kind of a formal phrase. It's sometimes difficult to understand, but that means when you have a distribution that's not exactly normal, it still works well on it and it doesn't mess it up. It's pretty good even if you don't have an exactly normal distribution. So robust against a departure from normality. Okay, so let's look at an example of how this would work. So I know it looks like there's tons of words on the screen, but it's partly because I just want to make sure it's big enough for you to read where you are. So if you have the times in sleep for randomly selected adults, okay, well, one thing I'm going to say immediately is that this is good. It's randomly selected. Randomly selected adult subjects included in the National Health and Nutrition Examination Study. Now, they're listed below. And here are the unrounded statistics for the samples. So here's actually the listing. Like they asked adults and somebody got 4 hours of sleep, somebody else got 8 hours, 4 hours, 4 hours, 8 hours. So if you took these values and you run the one sample statistics or one variable statistics, N is 12, you can count that. There's 12 different adults there. The mean time of sleep was 6.83 hours. And the standard deviation for this sample is right here with lots of decimal places after it. Now, a common recommendation is that adults should sleep between 7 and 9 hours every night. Use the p-value method with a 5% or 0.05 level of significance to test the claim. The claim is that the mean amount of sleep for students is less than 7 hours. Now, why is that the claim? Because up here where we calculated, or I had calculated the mean, it was less than 7. First of all, it is a simple random sample. It says so. We have to check that requirement. Now, the next thing is that it has to be normally distributed or n has to be greater than 30. Well, n is not greater than 30 here. So is it normally distributed? Okay, well, it doesn't say it's normally distributed. That would have been the nice thing if it had just said it directly. But since it doesn't say it, how would we check it? Well, it's been a few sections since we've done this, but in a previous lesson, we talked about how to check normality with a normal quantile plot. So if you open up when you're doing your homework, if you'll open it in StatCrunch, and tell it you want to do a graph, then there is a QQ graph, which is your normal quantile plot, and you can look at it and see how it goes. So actually, this is the result of that. Not with the line through it necessarily, but all these little dots would be your normal quantile. And so the question is, do they essentially fit a straight line pattern? So we've already determined that it was a simple random sample because it said so. But when you look at this does kind of fit a straight line pattern. As we increase on the x, we fairly steadily increase on the y's, okay? So it's going kind of just generally uphill, so we would assume, you know, the next values would be somewhere in this area. So that's how your normal quantile plot lets you look at it. On the other hand, if you would rather do a histogram, as you can see then, this histogram, it's not exactly normal, but it's kind of lower on the edges and then higher in the middle. So this one would also indicate that it's somewhat normal. So we're going to go with it's fairly normally distributed, even though we don't have n is greater than 30. So we've met our requirements. Once we've met our requirements, then we should be able to do the test. So again, I don't have all the paragraph up here, but this was those key numbers from the problem. So let's look at what we would need to do for each of these. The claim, again, was that the mean amount of sleep for adults is less than 7 hours. Now we're making a claim about a population, even though I only have a sample right here. The claim is that it is less than 7 hours. Well, then the claim cannot possibly be H sub O, because H sub O always involves an equal. So our claim is going to go down here and be less than 7 hours. And then our H sub O will be that it equals 7 hours. So you have no option on that. It has to be an equals. And one of these has to include the claim, okay? Now, alpha is this 0.05. So what we're going to do is, keeping these in mind, we're going to use the TI-84 t-test. So I'm going to pull up my calculator. And to get to that t-test, it is stats and then test. And then see right here, number 2 is a t-test. So now I actually don't have, I could have put in, like in my list, all 12 of these entries. But since this summary information was given to me, I'm going to go with stats. What is my initial information that I'm going to do? I've got to change all this. This is just pre-filled in from something else. My H sub O, which goes along with what they're calling mu sub O, is that it is equal to 7. What is the X bar for my problem? That is this 6.8. And it's not going to make too much difference how many decibels you put, but you wouldn't want to round it too early. So I'm actually just going to put 8 and then put several 3s after it. I never have to round my results to 5 decimal places. So going out 5 decimal places here generally means that when I get an answer, I'll be able to round it to 2, 3, or 4 with pretty good accuracy. My sample standard deviation, which is tucked away right there, is the 1.9924. And again, I'm just, maybe I'll go one more. It would round to a 1. But I could have put all those values in. And then, and I'm going to show you that in just a minute, I had 12 values for my N. Okay? So what is it that I'm testing here? I'm actually doing a left-tailed test. So I'm going to go over and say, I'm saying that I think it's less than what I put up here. So notice I put the 7 up here for my mu sub 0, and I'm saying that I am testing that the actual mu is less than that 7, which was mu sub 0. I don't need to draw this, so that makes no difference, but I want to calculate it. So when I hit enter and I get this result, these are the very important numbers for us. My test statistic is that T, so that is negative 0.2897 is going to round to 290. My p-value is 0.7773. So we can make a conclusion from either one of these methods. In general, the easiest method when you're using these calculators is your p-value method. Let's just go through this. Over here, I wrote this in and you saw me get it off the calculator. Okay? So 0.290 and 0.7773. 0.290, and I think that's a typo, but let's just pull back up that calculator. 7774 actually. Okay, so that was a typo. Where did that come from? It's craziness. 7774. Let's pull it up one more time. P-value 777, and that would round to a 4. Okay, So I have this information from my calculator. Now, what I haven't shown you is this critical value. If you're going to use the critical value method, you have to get a critical value from your calculator. And you do that from inverse t. This is kind of what we're looking at then. If you go over here, we end up with a critical, what we're saying is that it's less than. That's why it's a left handheld test. Alpha is 0.05, so that means we're looking at this area in our critical area as being 0.05. The critical value is the line that separates this 5% from this 95%, and you get that from doing inverse t. So how do I get to inverse t? I'm going to quit this one, and I'm going to do second vars, and inverse t is option number 4 right here. Now the area that's from the left, and inverse t always comes from the left, is 5%. My degrees of freedom was n minus 1, so since I had 12 values, I have 11 degrees of freedom. So you can see right here, that's exactly what I've put in. And so then when I go down to paste, it just copies it in a different format to my main screen. And I get this value, negative 1.796. So that's where this red critical value came from. You can't use the critical value method unless you also find the critical value from an inverse. And a critical value always comes from an inverse. Okay? So what you want to do is determine, okay, the critical value, which is this 1.796, is where we kind of have the cutoff line. So then you want to look at your test statistic and find out, is it in this critical region? Well, negative 0.290 would actually not be in that critical region. Okay, it's just slightly to the left. I would have to be over here like negative 1.8 to be in the critical region. So you only reject the null if you're in the critical region. Since I'm not in the critical region, my conclusion would be fail to reject the null. Remember, your conclusion is always about the null. You either reject or fail to reject. So I'm going to fail to reject H sub O. Now, what does that mean as far as the interpretation? The interpretation has to be about the claim. So if I am not rejecting the idea that the average or the mu, the mean, is actually 7, then there is not sufficient evidence to support the claim. Now, we're not rejecting the claim because what we're just saying is there's not enough evidence. We'd have to interview more adults, get another survey, get a larger sample, okay? So there is not sufficient evidence. You always use something about evidence in your interpretation to support the claim. And I'm going to stop right here because writing on this is such a pain, but if I were choosing a sentence or writing out a sentence in a report, I would say there is not sufficient evidence to support the claim that the mean for the adult population is less than 7 hours of sleep. So that takes us through the critical value method. When you're using the critical value method, you have to use an inverse to get a critical value, which is your cutoff line. And then if your test statistic falls in the critical region that gets cut off, reject the null. If it does not fall in the critical region like ours did, and it was somewhere in this area, since it's not in the critical region, we fail to reject. Okay, let's look at the same example. Let's just talk about the p-value method. The way you decide if you should reject the p-value method is that if your p that you get from doing this is why I like this one better, because you don't have to do that inverse t. If you get a p-value that is less than alpha, then you reject the null. So here what I want to do is look at this p-value 0.7773 and compare it to, that's my P, okay? Compare it to the alpha, which was 0.05. And actually, P is greater than alpha. So because of that, I'm going to, again, fail to reject. Now, both of these methods should give you the exact same conclusions. They should give you the exact same interpretation. The reason you have to know both methods, and honestly, you've got to know what this test statistic is and what the p-value method and things, because they're going to ask you both ways on the homework. But if you're not sure of yourself, if you're not sure you're making the right conclusion with the critical value method, then just this is the easy one to understand. If the p-value is low, H sub O must go. Okay, so again, we're going to say there is not sufficient evidence to support the claim. So p-value, if p is smaller than alpha, you reject H sub O. Your interpretation always has to be about the claim. There is sufficient evidence or there's not sufficient evidence, okay? If you're using the critical value method, on the critical value method, if your test statistic is in the critical region, which you get cut off by the critical value. It doesn't look like an I, does it? That's when you reject the null. Okay, so let's do another example. We'll go through this one more time then. Is the mean body temperature really 98.6? I know I grew up with my mother telling me it was 98.6. And those of you that had your temperature taken a lot of times during the COVID pandemic, before you could go in someplace, have probably been a little bit surprised at the number of times your temperature was definitely below that. Now, some of that may be due to the type of thermometers that they used. However, watch what happens here. There is a large data set in Appendix B of the textbook. So if you went into the online text, you could see a large data set. But rather than try to put all that here, what I'm just going to tell you is that it does come from a simple random sample. And here are the statistics for one particular day of it. N was 106. Now, the mean temperature was 98.2, which is a little lower than 98.6, and the standard deviation was 0.62 degrees Fahrenheit. We're going to use a 5% significance level to test the common belief that the population mean temperature is 98.6 degrees. Okay, first of all, requirements. It is a simple random sample. They said so. And we definitely have 106 for our N. They said so, so we're greater than 30. So we've met both requirements. Okay, we didn't have to do any sort of a quartile viewing or anything like that, or quantile viewing, excuse me. This is, again, that key information. So let's go through this process. First of all, what is the claim? We are supposed to test the common belief that the mean is 98.6. So that's our mean. And forgive me for not writing degrees Fahrenheit over and over and over. It really does apply, but I'm just trying to save some writing. Now, since this one involves an equal, that's also going to be my null, because the null always involves an equal. And somewhere you have to have the claim involved. Okay, so if this is my claim, then this one will just be the opposite of it, which means that it is not equal to 98.6. I don't know what that was about to be, a hook or something. okay? But it's not equal. So if your claim involves an equal, you put it here, and then your null is your alternate is the opposite. If your claim does not involve the equal, then your claim is H sub 1, but your null is still that it equals. Okay, they told me up here that alpha was 0.05. It doesn't have to be, but that is extremely common. Now, if I'm going to get critical values, again, since I don't know sigma, I just have S up here, not sigma, then I'm going to be dealing with inverse T. However, for those critical values, notice that this is a two-tailed test, which means if you could visualize this, I have to have a section with a critical region over here, and I have to have a section with a critical region over here. Since alpha is 0.05 altogether, then that means that this must be half of that. So like alpha over 2, which means this tail will involve 0.025 in the tail, and this tail involves 0.025 in the tail. So don't forget, when I pull up this inverse T to get my critical values, I have to do an area to the left. So when I put in this value, it's going to give me this number. So let's pull up the calculator, and I'll clear this, and we'll do inverse T again. So that is second vars, which brings up distributions. Inverse T is number 4. The area to the left right here is 0.025. And my degrees of freedom is n minus 1. N was 106, so my degrees of freedom is 105. So this value right over here, the critical value over here on the left, is negative 1.983. Negative 1.983. Now, I can also then get this critical value by saying, well, if I have 5% in the tails, this center section had 95%. So if I'm coming from the left, this area would be 95, 96, 97. So it'd be 0.975. Okay, 0.975. So if I do that again, and I put 0.975, same degrees of freedom. Now what you're going to see here is that I really didn't need to do this. Because this thing is symmetrical, if you have a two-tailed test, the value on the left and the value on the right will be opposite. So you're going to get plus and minus. You do need to remember, though, that if you have a right-tailed test, you would have to do this possibly, you've got to always put in that area from the left on this inverse T. All right, so the other area that I have over here then is actually the positive. So I'm just going to put plus or minus 1.983. Now, if you're entering it online, you might have to put a comma in between them, or it might ask you specifically what the negative one is or the positive one. So now we're going to do the test to get this information. So I'm going to pull that back up. And we're going to do the test at, that is stats, over to test. The t-test is number 2. And I am entering statistics because I'm not entering the large list of numbers. My null hypothesis was that it equals 98.6. Okay. The mean from the sample, that's up here at the top, was 98.2 or 98.20. The sample standard deviation was 0.62. Again, that's already calculated for me. And N was 106. Now this is actually N, not degrees of freedom, because the calculator knows that it needs to do degrees of freedom. My alternate hypothesis this time is that it's not equal. So that one's set correctly. So I'm going to go down and calculate. So again, I'll need to write this on the screen. It's going to go back and forth. But this one is the negative 6.6423, so that's my test statistic. My p-value is essentially 0, and at first glance it might not look like it, but do you see this e to the negative, e to the negative 9 right here? You need to look closely at these long decimals. If you have an e at the end, a negative means that the decimal place needs to move 9 places to the left. If it were positive, we'd move that decimal to the right. But 9 places to the left means I'm going to have 8 zeros in front of this 1. So this is going to round to 0. Not exactly, but it's going to round to 0. So I'm going to move this out of the way so I can write this stuff down, and I just put it on my other screen so I didn't have to click back and forth. So my test statistic is negative 6.642, and my p-values generally go, test statistics we usually take 3 decimal places, z-scores are 2 decimal places, and p-values are 4. I'm so sorry. But that, at least on your homework, it normally tells you what to round it to. But this one is really going to round to 0. So now I think our next 2 slides is looking at this from different perspectives. So before I write the conclusion and interpretation, I have to remember what was on my next slide. Yeah, so I just only went to 2 decimal places here. But because that was so extreme at negative 6, that's going to be okay. A p-value of 0 is like that also, because what this really means then, and I have my critical values here. Did I have those critical values written correctly? Yeah. Okay. What that really means, if we're using the p-value test, if you're going to test by p-value, if p is less than alpha, and this value is less than alpha, because my alpha was 0.05, right? If p is less than alpha, then H sub O must go. So we are going to reject the null. So we are rejecting that it's actually 98.6. And the interpretation is that evidence seems to support the claim that it's not equal to 98.6. Okay, now we didn't, that was, even though you might say, well, it's less than. No, we didn't test that. We just tested that it's not the same as 98.6. We did reject the null, but the null was the claim this time. So I have got to rephrase that. There is not, you got to look closely at what that claim was. Not sufficient evidence to support the claim. And to clarify here, that's why I always write down what is the claim. The claim was that it's equal to 98.6. So we are not going to support the claim that the mean is 98.6 degrees Fahrenheit. Okay? Evidence suggests that it's not. That's it doing this. Now, what if we did the critical value method? Now, I don't use that one as often, but again, on that critical value method, what's happened is we've cut off 2 tails. This one had the negative critical value, and this one has that positive critical value that you can see right here. So not quite at plus or minus 2, but awfully close to plus or minus 2. These tails are then the critical regions. If your test statistic is in a critical region, that's when you reject. So we need to place this negative 6.64 on there. Well, negative 6.64, if this is approximately negative 2, negative 6.4 or 6.64 is somewhere way to the left of that. That is definitely in the critical region. And if it's in the critical region, you reject H sub O. So again, we get the same conclusion and same interpretation with either the critical value method or the p-value method. If you do the p-value method, alone, then you don't need to do that inverse t. If you're going to use the critical value method, you get your critical values from the inverse. Now, on your homework, they're likely to ask you to fill in all of these separate pieces. Okay, now the interpretation might be a multiple choice. The conclusion might be a multiple choice, but all of these other little things you're going to have to fill in or choose. I think the claims are multiple choice, or the hypotheses are multiple choice. Everything we did here was for if you don't know sigma. But what if you do know sigma? Okay, well, I'm not really going to take the time to do examples of this one, because if you do know sigma, then the idea is the same, but you're not dealing with t. You're going to use the z-test, which means it was normal, and inverse norm to get critical values. Okay, so if you knew sigma, then you're dealing with something normal, z-test and inverse norm. You probably do not know sigma, but that's the only difference. You still have the same requirements. You just use, instead of t, you use z. Don't forget, I'm happy to answer those. Ask my instructor questions if anybody's behind. We've only got a little bit of time left, so be sure you send me as many questions as you have. I'm here to help you. That finishes up this lesson.